Dear Sir or Madam, welcome to my presentation for a virtual international conference AEIT2020. My name is Pasquale Franzese from University Federico II of Naples, Italy, and I'm going to present charging strategies for ultra-fast stations with multiple plug-in electrical vehicle parking slots. Enjoy the video. The topic of my paper is the ultra-fast charging for electrical vehicles. The charging station in my university department has multiple plug-in slots to charge until 2 vehicles at the same time. The paper goal is showing how to plan the charge strategy for contemporary charging vehicles, ensuring an appropriate balance of energy and power between sources and loads. The charging profile planning for individual vehicles is related to the scheduling problems that involves all vehicles in station. The scheduling problem can be traced back to an optimization problem, and its solution influences the choice of charging profile planning. This cycle of operation is repeated for each vehicle. The paper and this presentation are composed by an overview on the context and the problem description, the selection of a suitable scheduling algorithm under certain conditions, the transition from the scheduling problem to the optimization problem for one or more vehicles, and finally the results and the validation of solutions are presented. The standard proposes a definition of ultra-fast charge, calling it mode for charge. The maximum values of voltage and current are prescribed, but also the properties that characterize the charge mode are indicated. The value of charge time has to be read as the time to bring the battery of vehicle from 20 to 80%. The constant current charge at maximum value is possible only in this state of charge area. All batteries from now on are charged and discharged in this considered area. The structure I'm going to present is a typical one in ultra-fast charging stations. There is a grid which can provide its maximum installed power. If the demanded power of the loads is less than the grid installed power, the grid can charge the vehicle alone. Since the demanded power can increase over that installed ones, the charging stations are equipped with a storage system that help the grid to fulfill the demanded power. When the vehicles leave the station, the storage system is charged by the grid at the grid installed power. The battery is sized based on the power of the grid, the power of vehicle targets, and the number of vehicles using the load leveling criterion. This criterion is based on the balance of the energy present in this equation. More in detail, the structure I will refer later on is that of the station in my department. A photovoltaic system on AC side is also connected to the network. The several converters connect sources and load. An active front-end is connected to the network to keep voltage constant on the common bus. DC-DC converters for a direct control of power which flows on the vehicles. A bidirectional DC-DC converter then allows the network to work at maximum constant power and the battery storage system to make up for the load power peaks. The maximum power value of the network is set to 100 kilowatts because the station is designed for low voltage connections. The charge profiles depend on the arrival time of vehicles, their initial state of charge, and the state of charge of the storage system for each arrival time. The management problem can be seen as a scheduling problem. In order to choose the suitable scheduling algorithm for the scheduling problem, we are going to analyze the charging procedure. The vehicle arrives at the station and provides its status information, state of charge, capacity of battery, and maximum value of power or current. The system processes these information together with the best status and the energy and power constraints, and results the charging profile. The customer receives the receipt with the charging profile and pace on the basis of charging time. A faster charge is a more expensive charge. The same procedure is applied to the second vehicle, but the energy and power constraints depends on the charging profile assigned to the first vehicle in this case. The choices on the first vehicle affect the charging profile planning for the second one, but not vice versa, because the first customer has already accepted the charging profile for his vehicle and he has paid for it. For this reason, the planning for the second vehicle is more constrained, so the performances of charge are less than that of the first vehicle. The scaling algorithm must be multiprocessing since there are multiple slots, non-preemptive because the performances assigned to the first vehicle cannot decrease in order to help the second one. Online, because there aren't a priori information about arrival times of vehicles. Optimum, because no heuristics are used. The choice of a suitable scheduling algorithm depends also on the constraints of the problem. The priority is given to the vehicles in the same order in which they arrive, because there isn't a provision on the arrival times. There aren't time constraints for not preemptive nature of the problem, and the resources constraints are physical constraints. The best candidate algorithm is first come, first served. A metric function can be used to evaluate the quality of the algorithm. In particular, the average response time can be reduced as follows. Reducing the interval time between arrival time and start time, but in the charging procedure this interval is already zero. Increasing the number of charging slots, but the solution can be useless because the charging performances depends on the resources constraints anyway. Relaxing the energy and power constraints, but the solution is expensive and it involves a consistent hardware change. As it appears, the reduction of execution time of each charging process is the best way to reduce the response time. The improvement of scheduling algorithm is led back to an optimization problem whose solution suggests a charging constant profile and the maximum value of the power for a charge with imposed power. For the first vehicle, the power constraints concern the maximum charge power on the vehicle side and the maximum values on storage system and the grid, taking into account the efficiency. If the inequality 1 is verified, the energy required by the vehicle is entirely contained in the storage system, so the charging plan can be done without the energy constraint. The energy required by the vehicle is proportionally distributed between storage system and the grid. If the inequality 2 is verified, the energy constraint is imposed to balance the distribution of energy between the storage system and the grid. It should be noted that if the inequality 2 is verified, the charge can be carried out, but with less performances. The conditions 1 and 2 allow to define two optimization problems with two solutions. In the first case, the charge power is chosen between two options. In the second case, there are three options. In second case, the presence of third term doesn't mean that the power is equal to this term, but only that the choice is more bounded. The optimization problem for the second vehicle is more complex than the previous one. On the basis of arrival time of second vehicle, three cases can occur. The charge, contemporary to the first vehicle, can be partial or complete. The degenerative case is when the two vehicles are never contemporaneous. This case is solved as for the first vehicle. If the second vehicle arrives at the station when the first vehicle is charging, case 1 cannot be easily distinguished from the case 2. The objective function is the same of that for the first vehicle, while in the power constraints there are both the power of first vehicle and the power of the second one. The inclusion of energy constraint depends on a condition. After the planning of charging profile of the first vehicle at the time t1, the energy from sources and load is exchanged at the time t2. At this time, the second vehicle arrives. If the inequality 1 is verified, the energy required by the vehicle is less than the energy of the storage system at the time 2 and the energy of the grid reserved for the charge the first vehicle. Also, if the inequality 1 is verified, the charge may fit both case 1 and case 2. In case 2, the energy reserved for the second vehicle is provided entirely by the BESS. In case 1, the energy reserved for the second vehicle is split between the storage system and the grid. In both cases, the energy constraint is not necessary. On the contrary, if the inequality 2 is verified, the energy constraint is mandatory. The condition 2 allows that only the case 1 occur. It should be noted that if the inequality 2 is verified, the charge can be carried out, but with less performances. The condition 1 and 2 allows to define two optimization problems with two solutions. These solutions are the charging powers of the second vehicle only in the case 2, because in the case 1 there is a time interval in which the second vehicle is alone in charge. In this final time interval, the power available by the station is higher than the first part of charge. In the absence of contemporaneous charges, the solution is the same than that formulated for the first vehicle. The solution results confirm that the charge of two vehicles is available in different conditions. In the case 2, for example, when the storage system is charged enough, the second vehicle can finish its charge before than that of the first one. In the case 1, when the BESS is charged enough, the optimization problem can be solved without the energy constraint. In the case 1, if the BESS is half charged, the second vehicle can be charged, but its charge couldn't fit into the typical charging time of ultra-fast charge. The loss of performances of the last simulation can be solved with a different scaling algorithm that can recognize the preemption and the heuristic approach. Using the proposed scaling algorithm, the loss of performances implies a subclassification of charge and a reduction of the income for the charging supplier. Thank you for watching the video. Don't forget to send your questions to my email or to those of the other authors. Have a good day. See you.